So let's say we're given this matrix, and we've done row operations where you can interchange the rows and apply operations to manipulate them. Does the same apply to columns? Can you interchange columns as well as apply operations to the columns as well? And it turns out you can. And operations performed in the columns of a matrix are elementary column operations. And two matrices are common equivalent when one can be obtained from the other by elementary column operations. So let's say we have this matrix right here. What happens when we interchange rows? Actually, what if we switch out columns 1 and 2? What ends up happening to the determinant of that given matrix? And it turns out, just like row operations and the determinant, when you interchange two columns in a matrix, the determinant ends up being negative. Okay, so what happens when we do some factoring? What does that look like exactly? So say we're given this matrix. Which of the three columns can we factor out a value? And if you were to say we can factor out 2 from column 1, you'd be correct. And it ended up looking like the following right here. And there you have it. So, let's see if we can progress with one more example, where we had to find the determinant of A using elementary column operations. So what can we do here if we were only limited to column operations? Well, let's look at whether or not the columns are factors of each other. Are columns 1 and 2 factors of each other, and if so, by what value? And it turns out the first two columns of A are multiples of each other, and if we multiply the first column by 2 and add it to the second column, what happens exactly? So let's see here. And we're going to change it, we're going to have it change column 2 based on the operation. So what ends up happening is the first column, hold on, I just need to make some adjustments here. But anyways, so the first column and the third column remain the same. And the second column is what changes here. And it turns out that while the first and third columns are the same, we get a column consisting of zeros. Well, now, what does this mean exactly? So if you were to find a matrix and you were to expand by columns, what does that look like exactly? What ends up being determinant? So let's remember here that at this point, it doesn't have to be written in triangular form because we have an entire column of zeros. And in this case, when you have zeros in this kind of sequence, what happens to determinant really? And mathematically, it ends up looking like this, where determinant of A is equal to 0 times the cofactor of 1, 2, plus 0 times the cofactor of 2, 2, plus 0 times the cofactor of 3, 2. And as a result, the determinant of the given matrix is 0. Again, you may have to go back a few videos and look at minors and cofactors. But what I'm simply doing here is I'm grabbing each entry within the second column and by grabbing the first 0, that's C1, 2, row 1, column 2, it's 0 times the 2 by 2 matrix of the entries not highlighted, and you do the same thing at column 2, row 2, column 2. We grab 0 multiplied by the remaining entries not highlighted, and you do the same thing at row 3, column 2. And it turns out 0 times anything is 0, and therefore the determinant of this matrix is 0.